Hi, let's take a look at section 3.1 where we're studying quadratic functions, and let's look at exercise 3.1.38. Here we want to use the vertex and intercepts to sketch the graph of the quadratic function. We want to give the equation of the parabola's axis of symmetry, and we want to use our graph to determine the function's domain and range. So let's first of all begin by writing this in standard form, where the exponents on the variable go from smallest to largest. Another way to say that is we're going to write it in descending exponent form. So this is our function f of x in descending exponent form. X squared minus 4x plus 6. So the first thing that we will do is we will determine which way the parabola opens. We realize that our function is actually given in the form ax squared plus bx plus c. A is the coefficient of x squared, b is the coefficient of x, and c is the constant. So we see that a is an unwritten 1, x squared is the same as 1x squared, b is negative 4, and c, which is the constant, is 6. So since a is bigger than 0, since a can't be 0, it's either bigger than 0 or smaller than 0 for a quadratic function, the parabola opens upward. So the sign of A tells us whether the parabola opens upward or downward. If A had been negative, the parabola would have opened downward. So now we're going to find the vertex. Since the parabola is upward opening, the vertex will be the lowest point on the parabola. If the parabola were downward opening, the vertex would be the highest point on the parabola. So in this case, the vertex is a minimum, or the y value of the vertex is a minimum. If the parabola had been downward opening, the y coordinate of the vertex would have been a maximum. So to find the x coordinate of the vertex, which we often call h, we calculate the value of negative b over 2a. And in this case, since b is negative 4, this formula gives us negative 4, and since a is 1, over 2 times 1. So this winds up being 4 over 2, which is 2. So the x-coordinate of our vertex, which we call h, is 2. Now the y-coordinate of the vertex we call k. And that's found by taking our h and replacing all of the x's in our function with h. A simpler way to say that is we're going to calculate f of h. Now we found out h is 2, so we're going to calculate f of 2 to find the y-coordinate of our vertex. So our function takes whatever you put into it, squares it, subtracts from that 4 times the input, and our input in this case is 2, plus 6. So we have 4 minus 8 plus 6. Well, 4 minus 8 is negative 4. And we need to add 6 to that to find k. So k is 2. So we now have the vertex. Our vertex is the point with coordinates 2, 2. So that's our vertex. And let's highlight that information. Okay. The other thing that we want to do is the problem told us to use the vertex and intercepts. So when we try to find the x-intercepts, those are the points of the parabola, point or points that lie on the x-axis. We do that by setting our function, which was x squared minus 4x plus 6 equal to 0. So whatever the quadratic function is, to find its intercepts, we set that function to 0. But there's something we should always do first before we go on a path of finding these intercepts. We first should determine, are there going to be any intercepts? It's possible to have 0, 1, or 2 x-intercepts. And we know that our parabola opens upward. We know our vertex is the point 2, 2. And what we find by looking at the y-coordinate of the vertex, we find that the parabola always lies above the x-axis. Since the y-coordinate here is a positive number, the vertex lies above the x-axis. Since the parabola opens upward and the vertex is the lowest point on the parabola, we know that all other points will lie above this lowest point, which means no point on the parabola touches the x-axis. So if we take a minute, once we know the vertex and the way the parabola opens, and we think that through, we can save ourselves some work. We aren't going to get any x-intercepts. What this means is, if we would have solved this equation, the function equal to 0, the solutions would have been imaginary numbers. That means we get no x-intercepts. In order to have x-intercepts, the solution or solutions have to be real numbers. If the solutions are imaginary numbers, then that indicates that the graph never actually touches the x-axis. And you can save yourself the time and work of finding those solutions that would have indicated there are no x-intercepts. Now there's always a y-intercept on an upward opening or downward opening parabola. And we find y-intercepts of any kind of function or graph of a relation by replacing x with 0. Now the nature of a quadratic function is such that if x is 0, the result is actually always going to be your constant of your function. So this is actually our value of C. So the point, since 6 is our y-intercept, the point 0, 6 lies on our parabola. And anytime a point has a 0 x coordinate, we know that point lies on the y-axis. So our y-intercept is the point 0, 6. And actually, since the y-intercept is different from the vertex, we have enough information to graph the function. It is possible for the y-intercept, or in the case of a single x-intercept, it is possible for that to actually be the vertex. If that was true, you would need an additional point to graph the parabola. But in the case where the y-intercept or the x-intercept is different from the vertex, once you have those 2 points, you have enough information to get a graph. However, if x-intercepts did exist, you would want to precisely know their values, or its value. And actually, whenever there's one x-intercept, that has to be the vertex. So in the case where the vertex is different from the x-intercept, there will always be 2 x-intercepts if there are indeed x-intercepts. In this case, there aren't. So the only thing we need at this point is the equation of the axis of symmetry. That was another thing we were asked to find. The axis of symmetry for a parabola that opens upward or downward is always a vertical line whose equation is x equal to whatever our h is. And in this case, h was 2. So our axis of symmetry is the line, vertical line, x equal to 2. So let's look at the domain, which the domain of a upward or downward opening parabola is always the set of all real numbers. So if we write that in interval notation, all x's that are real numbers can be given as input to this function and give us a meaningful result. So in interval notation, that's the interval where I can move indefinitely, anywhere indefinitely left or right on the number line. So we show that as negative infinity to infinity. Remember, infinity does not represent a number, but a pattern of behavior. So this says I can move on the number line indefinitely left, and I will have an x value that can be given as input to the function and result in a real number, or I could move indefinitely to the right. Now the range of an upward opening parabola is always all y values that are bigger than or equal to k. In this case, k is 2. And as long as I put in a y, no matter what x's I put in to this function, the y values that are going to result are 2 or anything bigger than 2. So notice the range will always be, if the parabola is upward opening, k or any number to the right of k, or any number above k, since we're talking about the y values. So the form of this type of parabola, the range of this type of parabola, is always all real numbers k and bigger. If the parabola had opened downward, the range would have been all real numbers smaller than or equal to k, because then k is the highest y value. When the parabola opens upward, k is the smallest y value. So that's always the form of the range for a upward or downward opening parabola. So that's something that always results. So I just want to highlight that as just information if you were working a problem where the parabola opened downward. All right, so let's look at graphing this. So here's an empty graph where I want to put my parabola. And notice, once I know how the parabola opens and I know the value of the intercepts and the vertex, I know how much of the xy plane I need to see. So notice this is a good window to have to illustrate what's important about this graph, because my vertex is the point 2, 2. My y-intercept is the point 0, 6, and my parabola opens upward. So notice my x values are that I'm going to show are going to merely range from -1 to 5, and my y values that I'm going to show on the graph, actually, because we know what the range is, are anything 2 or bigger. So I want to always show a sufficient amount of the graph so that you get a good picture of the graph. And I know the general shape of this type of parabola looks like this. So this is our y-intercept 0, 6, and this is our vertex 2, 2. And our axis of symmetry was the vertical line that has all x coordinates of 2. And the graph is symmetrical about this line. So if I move 2 units to the right of the vertex, there's going to be a point that's 6 units up. And that would be the mirror image of this y-intercept. So that's a rough picture of my graph. I actually didn't do too bad on this one. It can be sometimes a little challenging. One of the things you want to be careful of is that you don't make this look like a V. When you're sketching the graph of a parabola, you want to make sure that it's clear that the behavior of the graph near the vertex is a smooth turnaround. When the parabola opens upward, the function goes from decreasing to increasing in a very smooth fashion. So there's not a sharp turnaround. That's what a corner is. If I were to have a V-looking picture here, that would indicate a very sharp, sudden turnaround, sudden change in direction. But the function very smoothly makes this turnaround from decreasing to increasing. So you want to make sure when you show that vertex that you don't have a sharp point there. You don't have a V, but it should look something similar to this. And I can also use something like Mathematica to show this very precisely, and that's what I've done here. I've gone into Mathematica and I used the plot function to show this graph precisely. And notice how my drawing was not too bad. It it's a little rough. This is precise. And notice here I've highlighted the y-intercept, the vertex, and I've given the graph of the axis of symmetry.